Thank you everybody for coming today. So in our seminar, we have a Dr. Sthalibe Kolwa from the University of Johannesburg, and he's going to give us a seminar about AGNs and with the MIGHTEE survey. So thank you, Sthalibe. You can start now.
Okay, thank you very much, Edwin, for having me here, and thank you to all of those who've joined. So I figured that this would be a good time to give a review of all of the results that we've been able to publish so far from the MIGHTEE survey. I'm a member of the MIGHTEE working group, and we are focusing on studying galaxy evolution with our continuum spectral polarimetric and also spectral line H1 data product, and based at the University of Johannesburg, and I'm a lecturer. So the second half of the year, I'm actually teaching an honors course, so I'll have a bit more time for research. So I'm hoping to get some work published as well based on MIGHTEE survey data product. So to begin with, to give you an overview of the types of sources that we are interested in studying when we look in the radio continuum specifically, which is what we are looking at with MIGHTEE, radio continuum images. Active galactic nuclei are the first class of sources at a general level. They're very high speed particle accelerators, as we know, and they're powered by supermassive black holes that are between 1 million and 1 billion solar masses. Their cores, so these are their central engines. Our unified model of the active galactic nucleus tells us that the basic components of these objects are, as I mentioned, a supermassive black hole through black hole accretion and conservation of angular momentum and accretion disk forms, spins due to the spin of the supermassive black hole itself, and through a process of conservation of energy, black hole accretion results in the formation of bipolar jets, which are magnetized plasma systems that extend outwards at roughly 90 degrees from the disk axis or disk plane. And if we consider lines of sight to such objects, we'll be able to essentially classify, get different classes of AGN. And this happens as a result of orientation, of course, which is described in detail by the classic paper Unified Schemes of Radio Loud AGN. So when you've got type 2 AGN, you have your line of sight intersecting with the plane of the disk. And so you're seeing through the dusty torus, or rather, I should say, you're obscured by the dusty torus. So this broad line region where you've got ionized gas around the AGN is essentially not available for view, and the bright nucleus itself. However, when you look at an angle closer to the jet nucleus, the jet axis, you'll get a type 1 AGN. And these are generally called quasars. This is what we consider to be the quasar population. So in essence, your nucleus is exposed, it's naked. And then when you get closer to the jet axis, roughly between 15 and 20 degrees, as per definition, your line of sight is close enough to the jet axis such that you'll be able to obtain a gamma ray loud active galactic nucleus. And so the consequence of that will be a blazar, which emits in giga-electron volts and tera-electron volts. So essentially, AGN are multi-wavelength emitters, and the orientation in which you're able to see the AGN will define how it is classed. A second type of object that is ubiquitous within radio galaxies, specifically when you're probing down to very faint flux limits at the microJy level in flux density, are the star-forming galaxies. In this case, I've given an example of the so-called normal galaxies as Jim Condon calls them in his 1992 review. And this is M82. Although it's a star-forming galaxy that is regular, even within star-forming galaxy populations, this is quite unique because it's a starburst galaxy and it's forming stars very vigorously and very quickly. So it's high in stellar mass star formation rate. And these are also multi-wavelength emitters, of course. In the UV and optical, we're tracing young stellar populations. In the radio, we've got our non-thermal component, which in this case is from supernova remnants. in star-forming regions. And then we've got our infrared emission. In the mid-infrared, we'll be tracing dust grains where UV light is essentially re-radiated by silicates and graphite. And in the X-ray, we would have inverse Compton scattering of low-energy photons seeded from within the galaxy. And this scattering would be within supernova remnants where they're relativistic electrons. So within radio continuum surveys, essentially, we are tracing active galactic nuclei host galaxies as well as star-forming galaxies at the most basic level. So this allows us to gain insights into both nuclear activity and star formation rates. And when you are deep in your radio continuum, you're able to not just detect AGN, regular AGN that are loud in the radio, but also radio quiet AGN, as well as the low luminosity radio galaxies that previous surveys, such as those carried out with the VLA and VSS and FIRST, were not able to see simply because their flux limits were not deep enough. And then the star-forming galaxy population. So radio continuum surveys are essential for studies of galaxy evolution in general. And considering the fact that star formation rate is an important property of galaxies, and classically infrared luminosities have been used to constrain star formation rates, as we know from the Kennicott 1998 relation, we would need a dust-free measurement or calibration of star formation rate in order to properly understand how quickly stars are forming within galaxies, because infrared luminosities are impeded and affected by dust. And this is essential, of course, when we look at cosmic star formation rate density, and there's been some significant work to use MeerKAT imaging to be able to properly constrain detection. And given the fact that up to redshift 2, from the early universe up to redshift 2, 85% of the total star formation rate in the universe is estimated to be dust enshrouded. So deep radio continuum surveys will be essential in studies of galaxy formation, especially when we consider star formation. So here I've shown you a diagram where we've got published, ongoing, and also LOFA surveys that are highlighted on the plane of effective depth or sensitivity as a function of survey area. And as we know, there's a significant trade-off between survey area and RMS. So the wider the survey, unfortunately, the shallower, but that means that you'd have a wide sample of sources in order to carry out statistical studies that are very significant, or that will yield significant results. But over smaller areas, we are able to probe very deeply. And an example of that, of course, is our MIGHTEE Early Science Survey, where RMS depth to the thermal noise level is down to 5 microJy per beam. And our survey area, to begin with, was between 2 and 4 square degrees in the early science, but this will be significantly improved as more pointings have been added to our survey, forming the MIGHTEE Data Release 1, which will be published soon. The paper is being written up by Catherine Hale. So in the beginning, MIGHTEE was proposed as a MeerKAT International Gigahertz tiered extragalactic exploration among several other large survey projects to be carried out with MeerKAT over the next decade and decades. And the depth and wide field coverage over these 4 fields that are shown here is done, or going to be done, with the purpose of studying nuclear activity and star formation from the continuum product, H1 in galaxy groups and galaxies from the spectral line observations, and also magnetic fields from the spectral polarometric observation. And given that the fields that were targeted in the MIGHTEE proposal already have legacy observations in multiple wavelengths spanning from the X-ray all the way down to the far infrared, mid-infrared, near-infrared, and optical, as well as low and high frequency radio, we are essentially hitting the ground running with our work. So we have sources that are radio selected with MIGHTEE, and we can cross-match them, cross-identify them with already existing data. Of course, taking into account variation in angular resolution between frequencies and wavelengths, so that there is a requirement for deblending and other corrections. But the data is already there as far as the multi-wavelength ancillary detections go. And that is the case for COSMOS as well. So the XMM-LSS and COSMOS fields are, you can say, hotspots on the sky for studies of galaxy evolution, because there is such a wealth of multi-wavelength data already. So the MIGHTEE data release 1 pointings are shown over here for all 4 of the fields that were proposed. Also, the moon is given for the purpose of scaling, got a diameter of 0.5 degrees. Therefore, our MIGHTEE pointings are, you can say, roughly up to 2 square degrees in area. And you'll also notice that we've included a field over here, this square field. This is the area that's been targeted by the VLA 3 gigahertz COSMOS survey. And there is complementarity in area, of course, for MIGHTEE data release 1, that we have sufficient coverage now in the L band with MIGHTEE, which has a central frequency of 1.3 gigahertz. And also now we've got coverage at 3 gigahertz. So this increases our frequency, you can say, detections in the radio, which is important for radio spectral energy distribution formation, for instance, that allows us to study properties of radio sources. And then the other 2 fields, XMM-LSS, Chandra Deep Field South and Elias S1, have also been targeted, as mentioned, and data release 1 for XMM-LSS has the observations and imaging complete. So that means our calibration has been done by Ian Haywood and team, and we are able to use the data products now. Imaging is still in progress for Chandra Deep Field South. This is a rather important field because it coincides with observations with the JWST JADES program, for instance. So there might be a potential to combine deep, now infrared observations and deep radio continuum observations as well to study nuclear activity and star formation in that field as well. So that is our coverage now for data release 1. But most of the science that we have so far that's already in the archives from MIGHTEE is from the early science survey, which was published in 2022. And for that, there was 1 single pointing on the COSMOS field, which is shown here, and 3 neighboring pointings on the XMM-LSS field. The integration time is quite impressive, I would say. Less than a day for COSMOS, just over a day for XMM-LSS, and this provided significantly deep data. When optimized for sensitivity, you're able to go right down to approximately 2 microJy, as has been mentioned before, but of course, the resolution suffers. So in order to improve the resolution up to, you can say, 5 arc seconds, a robust parameter of -1.2 and the calibration procedure can be applied. But this, of course, increases your sensitivity or decreases your flux depth, you can say. So there's always that trade-off. Depending on one's science goals, you would optimize either for sensitivity or resolution. And over here, I included a distribution of the pixel-to-pixel frequencies provided in the paper, which, of course, shows you that frequency is not uniform across the field in the same way that the uncertainties in flux density are not uniform across the field. So one often has to make corrections for both frequency and flux density, depending on the position of the source on the field. So from these data products, in fact, let me just go back a bit. Just looking at this COSMOS pointing, I believe the story is that Jacinta Del Hayes and Ian Haywood were just looking at the image, and identified these two rather interesting sources. They're not point sources, but rather extensions of continuous radio emission, and were puzzled by them and decided to do some investigating. So obtaining or trying to look for optical data that would give information about these two elongations of radio emission, they found from SDSS catalogues that these are indeed sources sitting at redshift 0.1, roughly redshift 0.2, and redshift 0.3, and they seem to be giant radio galaxies. Now, although the radio cores over here, as you see for both of these sources, are detectable in the VLA 3 gigahertz COSMOS survey, this extension of gas, or I should say this extension of plasma, right, ionized magnetized plasma, was not visible in the 3 gigahertz COSMOS images. And that is because the UV coverage of the VLA configuration for that survey was not sufficient for one to be able to resolve this low surface brightness radio emission. So in essence, MIGHTEE, in early science data, MeerKAT itself as an instrument, being sensitive to diffuse and extended emission because of its configuration of antenna, allowed the team to see these very interesting objects, and constraining the radioluminosities in the L band and looking at how those radioluminosities compare to the general population of giant radio galaxies, it's been found that these two sources occupy an uncommonly low in radio power region of the power size relation for giant radio galaxies. So while they are very extensive in terms of their radio emission, they're also low power sources. And again, this is unusual. You can see how underpopulated this portion of the plot is. So they're very big, but they're also very faint. So based on this, the prediction is that with further studies, there's a possibility that more and more low power and massive giant radio galaxies will be found. And based on some spectral age modeling, the source ages were estimated to be roughly 700 megayears. So that's a rather short time scale, less than a gigayear. That such an extensive radio morphology would form. And then some work was done to tie together X-ray emission and radio emission in galaxy groups. In particular, VLA and MIGHTEE data observations were combined for a sample of roughly 247 X-ray emitting galaxy groups that were detected with Chandra at XMM Newton. Now, what they found for this sample of galaxy groups is that there is a significant correlation between 1.4 gigahertz powers and X-ray luminosities integrated over this energy range, which they understand to be probing in terms of the X-ray emission being the intracluster medium. And this directly proportional relationship is indicative of the fact that at the intracluster medium level, AGN heating is responsible for heating up X-ray bubbles or X-ray cavities on the large scale, and essentially preventing cooling of gas. So this preventative, you can say, mechanism, of course we call AGN feedback, is evident within these galaxy groups based on these observations. Another significant finding that came out of the MIGHTEE survey was looking at the infrared radio correlation for a sample of star-forming galaxies. Now we understand that for star-forming galaxies, based on early results in the 80s and in the 2000s, that infrared luminosities are tightly correlated to 1.4 gigahertz luminosities when galaxies are star-forming. And in this, we can define a parameter called QIR, which is the ratio of infrared luminosities to radioluminosities. And understanding how this parameter evolves with cosmic time is essential in calibrating star formation rates from radioluminosities, because we need to know how the balance between infrared emission and radio emission changes generally across cosmic time in order to properly calibrate star formation rates from the radio emission. And so this study went and did that, and showing this QIR parameter as a function of redshift, they find that there's a weak dependence of QIR with redshift. So there's not much of a trend along this axis. However, when we consider stellar mass shown in the color bar, there seems to be a trend with QIR, such that the more massive galaxies over here shown in red tend to have lower QIR parameters. And the conclusion from that of the authors was that for these very massive galaxies, high in stellar mass, star formation is compact. In other words, your sigma star formation rate or your star formation rate densities, so that's star formation rate per unit projected area, is suppressed. And that in turn suppresses your infrared luminosity integrated and therefore your QIR. Now, in studying radio sources that are detected on our MIGHTEE survey, of course, our radio detections alone are not significant. So what we have to always take into account is cross-matching. And I mentioned this very briefly when we were looking at the available multi-wavelength ancillary data. So starting out with a catalog of radio components that would be identified with PyBDSF, you'd be able to apply this procedure to your image and find where your components are. Of course, these are not individual sources because sometimes an individual source can have multiple Gaussian components. So the trick then is to apply the likelihood ratio, the probabilistic measure that gives us our likelihood of finding a true optical near-infrared cross-match to our data, that's the radio image, and trying to maximize the likelihood ratio as quickly as possible based on the magnitude distribution of true counterparts, the distribution of radial offsets, and also the distribution of optical and infrared magnitudes for all the sources available. And this has been done for the COSMOS field as a pilot study. The likelihood ratio was applied, and this allowed us to successfully find cross matches up to roughly 1 arcsecond on the low and high resolution images in our catalog. And that has been useful in providing us with an understanding of where we are identifying actual counterparts and where we are not identifying actual counterparts. Of course, the visual inspection has been important in that as well. But when we go down to very faint flux densities, classical confusion limit, in other words, where our radio sources are so close to one another, it's hard to tell them apart, cross-identification, even with optical, becomes tricky. However, this cross-identification has been useful in bringing about science, such as this study, which was based on the radio-loud AGN population in COSMOS, using a multi-wavelength diagnostic criteria, several of them, in fact. AGN and star-forming galaxies were identified among the radio sources in the COSMOS field that are MIGHTEE detected. You'll notice 54% of them are star-forming galaxies, whereas 35% of them are AGN. So that's expected. And this has been predicted that as we go fainter and fainter in our radio fluxes, we begin to detect a higher proportion of star-forming galaxies. So using optical morphologies, X-ray luminosity cuts, the radio excess, which is based on a QIR cut, such that when we are greater than 0.43 dex below the best fit line of the QIR as versus stellar mass function, we are selecting radio excess sources, and that's described in Delvecchio et al. 2021, and also the mid-infrared color selection that we know from Spitzer IRRC color cuts that also selects mid-infrared AGN, and also a visual inspection of very long baseline array images allows us to see where sources are jetted, where they have actual morphologies in the radio, and where they are non-jetted and probably not likely to be AGN. So using the catalogues that come about as a result of these multi-wavelength classifications, this paper looked at the high and low excitation radio galaxy dichotomy, which has been well studied up to redshift 1, and that's outlined in this very popular review. High excitation radio galaxies generally have Eddington ratios between 1 and 10%, whereas low excitation radio galaxies have Eddington ratios below 1%. So the Herg, super Eddington, the Lurg, sub Eddington. And going on to take our MIGHTEE sources and classify them as radio excess sources, and for optical AGN or mid-infrared AGN or X-ray AGN when they're Hergs, and then radio excess sources only when they're Lurgs. This paper, and Imogen Whittam led this study to look at the Eddington ratio distributions for these two distinct populations. And while at redshift 1, there's a clear distinction between the Eddington ratio distributions, as we go further out to redshift 5, the distributions overlap very significantly, and it becomes more and more difficult to tell these sources apart, essentially, in terms of their Eddington ratios. And that's quite an interesting finding, because it contradicts, or rather, maybe not, doesn't contradict, but it shows us something new about high and low excitation radio galaxies. And here's some result published by Martin Hardcastle's student, was an attempt to understand whether there's a correlation between radio source size and spectral age, based on, of course, radio spectra. So here, Siddhant used Jaffe and Parola models and fit on a pixel by pixel basis fit these models to MIGHTEE, LOFAR, and GMRT data. So here, wide frequency coverage, selected 28 radio loud AGN host galaxies. That's only sources that were resolved, so that's why they're only a handful, you can say, in the sample, and managed to constrain the spectral ages up to between roughly 3 and 115 megayears, with a median of 9 megayears. Overall, the main result was that there's no clear correlation between resolved radio sizes and spectral ages. So this is something to further investigate. What essentially, for a radio source, drives its radio size? Is it how quickly it forms? It can't be if we don't see a correlation. Or are there other factors in place that drive the evolution of radio sources, in particular, how extensive they become? And here we have some work from a student at the University of Johannesburg, who is studying particularly the radio quiet AGN population in the COSMOS field using MIGHTEE early science data. And the two questions Sandor is interested in asking is whether radio quiet AGN follow the far infrared correlation, or infrared radio correlation, I should say, and also how can we calibrate the star formation rates for radio quiet AGN. And using the MIGHTEE early science data and the multi-wavelength ancillary data already available, Sandor has classified the source population and found that many sources in the sample, up to 42%, are radio quiet AGN, with about 36% being star-forming galaxies, and all the others being some form of AGN, either radio loud or mid-infrared. And the main findings, okay, shown here at the top, we have the far infrared radio correlation and radio quiet AGN are shown in green, the green distribution, and just from a visual inspection of the plot, many of the radio quiet sources follow the correlation, while radio loud AGN, shown in red, clearly lie away from that tight correlation. So clearly in the cases for radio loud AGN, you have additional, you can say, an excess of radio emission, which is attributed to the AGN itself. But for radio quiet AGN, it's either they are not jetted, so they don't have strong radio jets, or the radio emission is just at such a low level that they really do actually start to look like star-forming galaxies when you consider this relation. And then in terms of the star formation rate as a function of 1.4 gigahertz luminosity, the calibration of radio quiet AGN, again shown in green, seems to follow very closely the calibration of star-forming galaxies. And those are shown by the correlations. In the dashed line, you've got the star-forming galaxies, and in the red line, you've got your radio quiet AGN. So overall, what Thando is seeing is that radio quiet AGN have you can say, properties in the radio and in the infrared that are very similar to star-forming galaxies. And to extend our, you could say, frequency coverage with MIGHTEE, the uGMRT, Giant Meter Wave Radio Telescope, has been combined in a commensal observing program where Dharam V. Lal and Russ Taylor are spearheading this. And it's a good connection between India and South Africa as far as radio continuum observing goes, since they're both Southern Hemisphere. Well, at least GMRT is able to observe fields in the Southern Hemisphere that MeerKAT does. Okay, so here I've shown some coverage on XMM-LSS and also a comparison of RMS sensitivity for uGMRT compared to GMRT. Well, of course, uGMRT is an upgrade, so there's a higher sensitivity, and compare that to legacy surveys. So we are now looking at the radio source population in XMM-LSS using this new superMIGHTEE data set, and again, performing similar analysis, PyBDSF, to perform source finding, cross-matching with the optical, and using legacy radio continuum data such as that of LOFAR, and combining our observations to get as wide a frequency coverage as possible. This can be very important for studies of radio spectra. We consider spectral index and spectral curvature on star-forming galaxies and AGN. We can infer the radiative processes powering and absorbing the emission, and also understand the link between how the radio emission originates and properties of the host galaxies using our understanding of processes radiatively taking place within these two types of galaxies. And of course, spectral aging results in spectral steepening, which gives us different spectral shapes. And this is a preliminary result from a paper that I need to finish very soon, where I'm looking at spectral curvature, so looking at spectral indices in neighboring frequency bands and understanding the distribution of these different spectral shapes and how they correlate with galaxy properties. For instance, in this plot, we've got the spectral shapes as a function of source brightness, and we see the very bright sources are peaked. They have peaked shapes, and then the fainter sources tend to be generally steepened and inverted. All right, and then finally, to begin with the polarimetric studies with MIGHTEE, Leonard Heino, his PhD, is looking at XMM-LSS field and has identified to 15,000 sources, roughly above the 100 microJy per beam noise level. And from rotation measure synthesis, he's seen that up to 7% of these are polarized over a very wide field, covering the L band, and with our Stokes Q and U, also covering, having a very deep flux limit as well. And this is work in progress, and we hope to see a paper soon. So all in all, our deep radio continuum surveys are generally crucial for studying nuclear activity and star formation, specifically for sources that previous generations of radio surveys have missed. So those are the radio quiet AGN and the star forming galaxies. And with MIGHTEE, since it's so deep, we're able to now see these sources in addition to low luminosity radio galaxies and learn more about this population that has been up until now unseen in the radio. So our main findings were the giant radio galaxies, a serendipitous discovery, which is opening a whole new parameter space for studying giant radio galaxies. Also investigating AGN feedback in galaxy groups, now using sensitive radio continuum observations, looking at how the infrared radio correlation evolves. And there's a strong function of stellar mass, and also Hergs and Lurgs, and how their Eddington ratios are more similar than we thought, and some upcoming work. We've got the polarized radio emission products that Leonard is preparing, and also got some superMIGHTEE studies of spectral indices, and also Tando Mutugwane is looking at star formation rate calibration with radio emission. So there's plenty of exciting work that's been published, and that is in preparation. And also another exciting event is next month. There'll be the IAU General Assembly number 32nd event to take place in history, and also the first event of its kind to take place in Africa. And we will be hosting Symposium 394 called All Inclusive AGN. We'll be talking about all matters related to active galactic nuclei. And you're welcome to pop by if you'll be there, or register virtually and attend online. Okay, thank you very much.
Okay, thanks again to Sthalibe for the very interesting seminar. So we can have questions if somebody has questions. Otherwise, I have a couple of questions. Okay, so my first question is about the giant radio galaxies. So there has been, I think, a recent work in which they found with the lobe survey that these objects are in reality, they are not rare. They just didn't find them because of the lack of sensitivity to the faint diffuse emission. They are more
Yeah.
they are more common than previously thought.
Yes,
So
I think that, yeah, that definitely, that's a great point. That it essentially instrumental bias was affecting the demographics of giant radio galaxies. That they were just too faint.
Yes, you just were lucky that two of them were in your observations.
Yes, and yeah, and just into and yeah,
And the,
yeah, the
at the
work that
other
you
point, yes, and the other point was about the far infrared radio correlation and the radio quiet quasars.
Mm-hmm.
So I did a previous work about doing this, but using image stacking
Mm-hmm. Mm-hmm.
and not this plot, the other one, which the ones that it says is from the student, which has the different frames.
Mm-hmm.
Yes, this one. So the thing is that if you do that with using the infrared, yeah, the stack infrared
Mm-hmm.
flux and the stack radio fluxes, you get
Mm-hmm.
basically that radio quiet quasars follow very tightly this the far infrared radio correlation. Basically, they lie on the line.
Mm-hmm. Okay, so that's when you stack the infrared and also the radio
Yeah,
emission.
yeah, yes. So what I got is that basically it looks like I'm plotting the quasars over the far infrared radio correlation on purpose.
Mm. Okay.
So,
Right.
so
That's yeah. It's
yeah,
almost
but of course
contrived.
I'm not doing that. It's just that it looks like that, and So you can put a constraints on the fraction of the on the total radio flux that is coming from star formation and AGN activity. So you can, assuming that the far infrared radio correlation is correct, you can put
Mm-hmm.
um, a percent
Mm-hmm.
a weak constraint on the percentages, and what also
Mm-hmm.
yes, and of course the radio detected AGNs, they have the excess that you expect.
Mm-hmm. 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 Okay. All right. And you've done this before. Is it published work?
Yes, it's published,
Yeah. Okay. We'll look at the paper then. Okay.
and yes, that is very interesting. Yes,
Mm-hmm. Okay.
yes. I don't know if there is any more question or comments from the participants. I don't know. Otherwise, we can. Okay,
There's
Vanelli has.
vanilla.
Yes,
Vanilla.
go ahead, Vanelli.
Okay, thank you so much for the nice talk.
Mm-hmm.
About the giant radio galaxies, like how did you calculate the redshift? I didn't understand the
Okay.
procedure followed.
Okay. So the optical redshift, the trick was to identify the core of the sources. So I believe that they began by trying to find where the active galactic nucleus should be. So looking at the high surface brightness peaks, for instance, in GRG1, you've got a hotspot here or high surface brightness peak here, and then another one here, and then another one here. So a lot of it is assumption that you would assume that if this is the extent of the radio morphology, then this must be the radio core, if we consider this to be a Fanarov-Riley 2 type of source. And a similar procedure was applied to GRG2. You'd find that there's a high surface brightness spot here, another one here. Here it's not so clear, but I guess considering the extent of the radio emission, they assumed that this must be the core. So there is there's a lot of assumption in that regard. So finding where the core is essentially of the active galactic nucleus. But once you've identified the core, then it's a matter of looking at optical catalogues. In this case, SDSS DR14, data release 14, provided the redshift of GRG1, and in GRG2, the Z Cosmos bright source catalog was used to find the redshift of the source itself. So essentially, you identify the core position, and then you look in optical catalogs for cross-matched or counterparts in the optical, and see if there are spectral or photometric redshift
Okay,
available.
okay, thank you so much.
Okay, yes, sorry, my screen just crashed. Okay, I don't know. There is a, I don't know. Vanelli is over. There is more questions, no? Okay, otherwise we can say thanks again to Stabili, and good luck with your talk in the UK. And so see you around. Thank you very much.
Yeah.
Thanks everybody. Bye.
All right. Thank you very much. Have a good afternoon. Have a good weekend. Bye-bye.
Bye.